Okay, so we are live now. Thanks, Prithen. Welcome, students, for Embedded Software Office Hours. We are live on Wednesday. I hope you all had some kind of a fall break here on campus. We had a fall break for on Monday and Tuesday. So we are back, and that's why we had to change the timings of office hours just for this week, so as to take care of the fall break. From next week, anyway, we'll be back on our normal timings on Mondays at 1 o'clock. It was just for this week. And we'll be resuming our normal schedule from next week. So we'll, as usual, start with some announcements, and we'll take some questions. And then we'll wait for some more questions from your side. So I hope all of you are progressing well on your project. Saw some questions about some issues about some scripts and other things. I hope the access to Deep Thought is fine now. Again, as we encourage you to take a private copy of the whole Valgrind and then Vagrant on your local machine, and then work off there and periodically sync and test it there on Deep Thought. That's the way it should be proceeding. Sometimes Deep Thought is down. There are no, some nodes are down, things like that. Sometimes the connection might be slow, so it is better. Okay, and that's, I would say, the best way to deal with this Deep Thought issue. And I guess I hope all of you are pacing properly in terms of your schedule there for the course. You should be starting to read now the papers. Again, I would like to say that the papers are quite important because they will be on the finals, and they, along with the paper itself, you have a lesson there which you should really go through that lesson first, the video, and then read the paper carefully. The best way to deal with it is to try to solve some examples which are relevant to the paper, try to exercise the algorithms in the paper, try to understand the concept. You all have familiarity with now the concept of course, the live ranges, interference graph, and the analysis that is needed for determining the live ranges and so on. So with that knowledge, you should be ready to tackle the papers because they pretty much use the same example in terms of understanding of the paper. The same concepts are used there. So please work through the reading of the papers. They're gradually exposing you to some things which are based on mainly register allocation. A lot of them deal with register allocation. Some of them deal with the assignments to different banks. And so there are some variants of the problem. So as you will see, if you take some examples and work your way through, do spend a little bit of time on understanding the papers, especially using the examples, and keep pacing it as per the schedule. We are done with 2 homeworks here. We are not assigning any homework for a little bit of time to give you some time to complete your project 1. And the project 1 has 2 parts. One is about the scheduling part, and the second one is about the speculation part. Both are very interesting and very important. They are really used in all the embedded software in terms of doing the instruction scheduling, and also the speculation is present in many processors. So even outside of embedded, the instruction scheduling in the presence of speculation, and how to handle the misspeculation by putting code which corrects the misspeculation is very important. So we have given details of those over there. There were some questions about what is the dependence, memory dependence, and register dependence, and some questions about dependence. So I'm going to clarify some of these things a little bit. So register dependence are pretty visible and are very clear and are completely known. Because if you use a register, read from a register and write into a register in the assembly code, you know that you have a dependence. It's either read followed by write, or write followed by read, or write followed by write. And those dependencies prevent, of course, motion of instructions over each other. And the good news about them is they are well known, they are open, and they are known at the compile time. However, that is not the case with the memory dependencies. So suppose you have a store into a particular memory location, and you have a read from another memory location. So you typically have base plus offset kind of addressing here. And the offsets are typically unknown, although the base pointer may be known of a particular array or whatever structure. The offset is unknown, and that's why when you do the instruction schedule at the compile time, you don't know if there is actual dependence between the two memory locations or not. So if you have a store followed by a load, then you have to assume that there is a dependence, because if there is at least one instance of a program in which you are storing in the same location and reading from the same location later through another load, then there is a dependence, and you cannot assume there is no dependence unless you are able to show that there is no such case. So that particular example would be that if you have a different offset, which is compile time known, you are reading into a location which is 10 units away from the base, and another one you're reading is 15 offset of 15 away from the base, then obviously there is no dependence. But 10 and 15 are compile time knowns here, which allow you to do this resolution. Most of the time that is not the case, because you compute the offset through the registers and things like that, as you see in the VEX code that is generated. And so you have a may dependence. So a may dependence you have to assume, and you have to construct the dependence graph, and from there then you have to do the scheduling. So we have given you the APIs and all to construct the to do the necessary stuff, some skeleton code. From there you build the dependence graph and do the scheduling. I hope all of you are well underway in terms of doing all this. From there you have to build the reservation table of which is shown in the book, and decide the resources which are available, which are given to you in the VEX, and from there to the execute the algorithm, which is based on the critical path, and then try the two different variants of these and so on. So it's try to take one step at a time and debug it. Make sure you follow a small example. First do it on paper, and then you can execute the algorithm, check its output, and make sure it is compatible and so on. And that would help in terms of doing the code. I hope all of you understood what is the topological order. It is in terms of the levels from the root. And the idea is, of course, to visit everything at a particular level before you move on to any node at the next level. And the book talks about the critical path scheduling and so on. I hope all those concepts are clear in terms of critical path is the longest path, which has the longest latency in terms of following the dependencies, and that is the lower bound on the schedule. So you cannot have a schedule which is better than that. Of course, in terms of if you don't have any resource constraints, you can come up with a schedule which is equal to the critical path, but that's not the case at all. In most practical situations, you have lesser resources, and in such cases you have to follow a heuristic approach, because the general problem is NP complete, and they have given you two different approaches. One is the generating the priorities using the critical paths ready to execute instructions and putting them in the next slots as per the critical path. If the critical paths are equal, then you have to go and do the tie breaking And that's where your other things come into picture. There is a heuristic which is given to you in terms of it's given to you in the book in terms of the utilization of the units, dependent instructions, and so on. And the other one which we are given you is in terms of the fan out, the highest fan out first. So those are the tie-breaking things which we are asking you to do. And then the second part of it is even more interesting, which is to go and move these instructions by first removing some of these memory dependencies, which are may dependencies, scheduling them as though they were absent, and then accounting for them at a later point in case your speculation was not right by putting the fencing instruction. So follow that example, and you are welcome to implement it in different ways. We have given you one implementation, and then check if the speculation helps or not. In a small code, small test example, you may or may not see the benefit of it, but the concept should be very clear, and speculation does help a lot in practice because many dependencies are, memory dependencies are really false dependencies. They are non-existent, but you have to assume them. But in case they happen to be true at runtime, you need to correct them. So the code is unsafe otherwise, and so that is the case. There was, so I'll pretend you have any things further to add in terms of grading or any announcement to make, and then I can take the questions, which one of them I see here, and the other one which was you emailed me. So go ahead and say whatever you need to say about grading or any other announcements.
Yeah, I don't have any further announcements. Just the homework 2 gradings. I mean, it should be out by next week. So the homework 2 gradings I have already started, but you have some things are left. So by next week it should be done.
Great. Thank you, Priten. Our other TA, head TA, Vincent, is on travel, so he's unable to join for this particular office hours, and perhaps the next one on Monday, but then he'll be back. If you have any questions or any emails you might have sent him, please send it to both of us so that you're not held up there, because he may not have an internet access. He's during the travel. Okay, so now I'll take some of the questions. There was a question about which was on Piazza. I guess somebody is not able to come on the office hours today, so I'll start with that question. This was a Piazza post 157 in terms of the tie-breaking rule. So there is a tie-breaking rule that is used, of course, trying to use the critical path scheduling as the criterion. At every point, you find out what is the most longest path, and you schedule those instructions in the available slot. So that's what that's per the book algorithm. But then the tie-breaking rules say that there is a unit ratio rule which is given in the book, or the fan out when operators share the same latency of the critical path. They may have the what to do in such cases, and how do these rules differ in terms of resolving the critical path. So they will not be, so the clarification is this, that these rules are there just to bias the schedule in terms of giving preference to what may happen after this particular point, but there is no guarantee. Remember that the critical path heuristic is only a heuristic because of the resource limitations. So if we don't have resource limitations, then the critical path heuristic guarantees, because it is always able to make sure that no instructions are held back at that particular point when they're ready. So that guarantees the meeting the schedule length equal to the critical path. So that guarantee exists only when there is no resource limitation, when we have lots of resources. But when there are only certain number of adders or any function units and things like that, or number of loads have to be limited because of the memory units not being available more than a certain number, then the critical path heuristic breaks down. It is no longer giving you any kind of guarantees. So these tiebreakers are used only to give you heuristic advantage. There is no guarantee that the critical path will be reduced or will be improved in future or anything like that. You definitely can find counter examples which the bias introduced by the heuristic in terms of taking those instructions which higher fan out may not work. So that's the nature of the heuristic. The intuition, of course, as you can clearly see here, is that if you give a preference to an instruction which has a lot of dependencies on it, then most likely all those instructions will not be held back and so on, and they will be scheduled without delaying them more. Whether this actually works better always, no, there is no such guarantee. And if you really want, of course, such guarantee, then the problem becomes NP complete, and you have to try out all possible different varieties of schedules and then pick the one which has the least latency. There is no other alternative to it. This is just a heuristic way of giving you bias, and it does not per se further critical paths or gives any kind of guarantee or any such thing. It's just a sort of maybe a common case that lots of instructions which are dependent may not be held back and so on there. So that's basically how things will work. So the flow of applying these things will be to start with the prioritized ordering is what you have to visit the nodes in that particular order. Okay, so at each point, of course, you have to find out the one which has the longest critical path and go ahead and schedule that. But in case there are multiple candidates which are ready to schedule instructions which have the longest latencies, then what you do is you pick the one which has longest fan out as the one prioritized over that. Over the other, and visit that and do the scheduling of that, and then visit the other. So the algorithm, as you see in that particular figure in the book, is sequential. It is visiting the nodes in that particular order, and the order is decided as follows. At every point, whatever is the longest critical path is the one which is used. The node is scheduled. That's the highest priority. But if there are multiple ones which meet that criterion, then you select amongst them the one which has longest fan out in another case, or the, as per the original heuristic, longest unit ratio and things like that. So that's the way the algorithm is to be applied, by determining this priority and then doing this in the topological order. That's you had to follow that as the ordering of the algorithm. So I hope this particular post is clear. If you have any further questions, you can clarify. Maybe we did not understand the question very clearly. In case it is not resolved, please put it on Piazza, and then we'll take it up there and answer it more. So I guess somebody is asking a question regarding the reservation table format. Are there any specific format or the format part of the algorithm, or do you have any particular format for global reservation table? We are not prescribing any such format. I think it's up to you. We'll not be auto-grading it in some sense. So we'll be looking at your code. Please try to put some small documentation around or comments so that we understand how you're keeping the information and so on in your data structures when you design those and in the table. So, but we are not prescribing any particular format. Thanks for the question. So far, we have seen 2 questions. Prathen, are there others on the YouTube, which if you want to put it over here, I'll be happy to look up here on our private chat.
No, I don't see any further questions right now.
Okay. So I do want to thank our TAs, Prithen and Vincent, who are working very hard and doing grading and answering some of your questions and so on. And um, we will be staying on track, top of things at our point, at our end, and the credit really goes to them. Okay, looks like there is a question about general explanation for list scheduling. So list scheduling is a general method which is used for scheduling directed acyclic graphs in terms of minimizing their schedule lengths and so on. And the technique was originally developed by Ron Graham as part of his theoretical algorithms. Under certain circumstances, the list scheduling guarantees you a schedule which is no worse than twice the length of the optimal schedule. So that is one of the big results by Graham. I'll try to post a link towards that particular result. The way, of course, list scheduling does it traverses a directed acyclic graph, fulfilling the dependencies, which means fulfilling a certain ordering on the graph. So the ordering is, of course, in terms of from all the predecessors of a given node should have been scheduled before the node is scheduled. So that is one kind of an order. Now, the other kind of ordering will be, especially in our context, is that the node is really ready at a particular time before it is scheduled. So that puts another kind of ordering, which is slightly different because it also involves not just being scheduled, but also the nodes, the previous nodes, their results being ready so that this particular node is able to, in the DAG, is not held back or is not stalled or anything like that. So such different ordering constraints are computed. The graph is therefore visited in a particular order to fulfill these constants. And then there is a list of nodes from which one has to pick, because there could be multiple possibilities of things being scheduled in a given slot. And then there are multiple versions of this algorithm. Some of them don't assume any, they only assume a single resource. Some of them assume multiple resources. Some might have complications that certain nodes can go on only certain resources, those kinds of things. And so that becomes interesting for our case, because this particular node has, a particular operation where the function unit is available there, and so on. Those are the constraints which are used by the reservation table there. And in general, the idea is what we are seeing in this particular algorithm, where the list is prioritized further based on the availability of resources and priorities assigned to the nodes and so on. And then the schedule is undertaken to fulfill this particular priorities. And in general, in the presence of resources, as I was mentioning, you really do not have any such guarantees in terms of giving a lower bound on the schedule, or any guarantees in terms of the schedule and so on. So that is what list scheduling really is. And I guess it's a very useful method which helps you to come up with quite a good heuristic solution. There are also studies on list scheduling in terms of how effective it is. And it is kind of empirical result, of course, that many times the schedule is very good, although there are no bounds which are promised because of the lack of any guarantees on the general scheduling problem. So I guess that's what the list scheduling is. There is a good article which I just found on list scheduling. I'll put a link. But it's more theoretical. You don't have to get inside that in terms of the theoretical bounds and so on. That's more for those who are interested in list scheduling as an algorithm things. So, okay, so that's answer. I'll send a link to you, Prathen, and then post it. Okay. then I just sent you the link for list scheduling slides, actually, which should help in general to really understand it, because the book has dealt with it a little bit at a more abstract level, as is the case with the Dragon book. Doesn't get into lots of examples and all. So can you please post this link on Piazza for under the list scheduling. I send it to you on your Gmail.
Yeah, I got it. Yeah, I'll post it.
Yeah, so those will really help them to really understand how these instructions are, the prioritization and all helps. Right. Thank you.
Yeah.